Okay, we're picking up with 5.3 lesson notes, a quick video to finish the definite integral and antiderivatives. So we went over the basic rules again that we had in the last section, and then we used the rules for definite integrals to discuss how we would apply them to determine using the functional notation with integrals and find the area, if you will, or the answer to the integral using sums. But if you see D, E, and F, we were not able to determine what the answer is because we didn't have enough information. So with those, then we went over using the bounds for an integral. We're looking at the max and the min, like what could it be between, and I wanted to see if the integral could be less than, or to show that it was less than 3/2. And we were able to do that because the upper limit, the max was, and I did the max and the min, even though I really don't need the min for this, it has to be less than 3/2. The max area is 1.414 and the minimum area is 1.241, so it has to be less than 3/2 because that's 1.5, and if I look at the max value is square root of 2, so that's less than 1.5, so it has to be less than 3/2. Okay, and then we looked at the average value of a function and what it means, the average value being the average value of the y value for the function itself, even though we're looking at area, the integral. And it kind of makes sense if you consider looking at an area. If we know we have an area and the interval length is b minus a and f is the height of the function, then if we have area is equal to f times b minus a, then it would make sense that area divided by b minus a is then equal to some function value. So even just looking at a situation with area, it helps to clarify how we're getting our answer or what the answer means in the end. So then we have the mean value theorem for definite integrals is what is that? The average value. So this is really f average. F average is then f of c is equal to the 1 over b minus a times the integral of f of x dx from a to b. Okay, and so the capital F that I was talking about here is really the antiderivative. So then we made the comparison that, oh, that's the mean value theorem for integrals, whereas you remember that that's the mean value theorem as long as the function is continuous and differentiable. There exists a c on AB such that f prime of c has to be equal to the average rate of change. So the IROC is equal to the AROC. It's kind of a similar thing here, as we'll talk about. So we left off with this problem. Determine the average value of the function on this interval from -1 to 1. So my plan for this, first, is I'm looking at the average value of the function, and I set it up, and I get the function and everything in there. And then as we look at the 1 over 2 times the integral from -1 to 1 of 1 minus the square root of 1 minus t squared dt, I have to have a plan. So if you look over here, my plan to get the areas, I'm going to take the rectangular area, and that's in blue, and I'm going to subtract off the semicircle area, and that's in pink, and then I'm going to get the area under the curve, which is green. So the rectangular area then is length times width, so it's going to be 2 times 1. So that's going to, I'm just going to put it in as 2 times 1 here. And base times height, cancel. And then the area of the semicircle then is going to be 1/2 or pi times 1 squared over 2, so semicircle. So we end up getting for this 1/2 times 2 minus pi over 2, which then turns out to be, we want to find the average value. So the average value, remember, is what we're finding all the way through here. So we get then 1 minus pi over 4, and you can say pi over 4 is about 3/4, so your answer should make sense. I think that you get an approximate value of 0.215. So that would be the average value of the function on this case. So average value, f av, is approximately it would be 1 minus pi over 2, just to clarify, 1 minus pi over 4, and that's approximately 0.215, okay? Just to make sure we have that answered fully, okay? All right, so that one was And so we're often taking areas and adding or subtracting them. So now connecting the differential calculus with integral calculus, we have the derivative of the integral from a to x, where x is a variable here, of f of t dt is equal to f of x. So now it kind of makes sense when you take the derivative of an antiderivative, should take you back to the function, right? So let's take a look at this first. We have the derivative of the integral from 1 to x of x squared, right? Now up above here, I have the integral of x squared dx is x cubed over 3 plus c. So when I take the antiderivative, that integral is an indefinite integral. I have to have a plus c. I get the family of functions, kind of like when we were taking antiderivatives, right? Same thing. So when I have the integral of x squared, what I'm going to do is keep the derivative with respect to x on the outside, and I'm going to take this integral. So it turns out that I get x cubed plus x cubed over 3, and then I'm going to evaluate it from t. You got to watch out. See how I have x's here? I'm actually going to change this just so this is a little clearer. You don't want to have x's everywhere. So I'm going to get t squared dt. Okay, so then now when I get my answer here, so you very often see that we have this f of t on the inside, so I'm going to make that t cubed. I'm taking the antiderivative. Then I'm going to evaluate it and say from t is equal to 1 to x. Okay, so now what I'm going to do is still keep the derivative. I'm not going to take the derivative yet. And I need to take the derivative with respect to x, so I'm going to plug in x cubed over 3, minus 1 cubed over 3 is 1. Okay, so now I've evaluated that. And so what do we get for an answer? We get the derivative of just the x cubed, right? So the derivative of x cubed, oh, you know what, let me do this. Over 3 minus 1/3, one more step. So go ahead and take the derivative. So with this, we get that this is equal to x squared, and the derivative of a constant 1/3 is just 0. So we get x squared. So it's funny how, when you're taking the derivative here and you end up with the same expression, except you have a swap of variables here. Okay, so that's what that's going to turn out to do. And this is just an introduction first, where remember that this capital F, and I'm going to do this, this was the antiderivative. Oh, sorry, antiderivative, okay? Capital F stood for that. So the antiderivative of f, lowercase f, okay? All right, so for the next problem where we have the integral of sine x dx, we're going to walk through this, okay? And then I'm going to evaluate it with the capital F that I'm telling you. So this will be the first time we really walk all the way through this. So you guys have the integral from 0 to pi, make this a little bit bigger, 0 to pi of sine x. I always like to use the parentheses there on the integrand, dx is equal to. So when you're doing this, you're thinking, what is the antiderivative of sine? Well, that's going to be negative cosine. Because if I reverse it, remember, doing that think cycle, that means the derivative of negative cosine is going to be positive sine. Okay? All right, so now that we have that, now I'm going to say negative cosine x, and then we have from x is equal to 0 to pi. All right, so then what I'm going to do is I'm going to do an f of pi, capital F of pi, minus a capital F of 0. You have to be careful when you input 0, it's not always going to be 0. So remember that f of x here is equal to negative cosine x. All right, so I'm going to apply that. So I have negative cosine of pi minus a negative cosine of 0. So we get a negative cosine of pi is negative 1 minus a negative cosine. So in the parentheses, negative cosine of 0 is 1, so it's going to be a negative 1. So with this answer, you're going to get 1 plus 1, or it's equal to 2. So the integral from 0 to pi of sine x dx is equal to 2. And then what you also have, you have your calculators where you can check that yourself and do the second calc 7, or you can do math 9 and plug your numbers in. You'll get 2 for an answer. Okay? So that's your first step into antiderivatives. And then as you look on the last one on your own, you can do this at home. So you're going to be thinking backwards. So for instance, here you're going to have a 5x, and then you're going to evaluate it from -2 to 6. So that you would just take the 5. So what we're doing is we're taking the antiderivative, and we don't have to include the plus c because the plus c would subtract out if you're evaluating it at 6 and -2. So we have 5 times 6, and that would be minus, it's always f of b minus f of a, so minus 5 times -2. Okay, so in that you get 30 plus, it's going to be 10, so we get the answer 40. Okay, so I'm going to set the next one up. So you're going to have 3x cubed over 3, and then we're going to evaluate it because we're using the x to the n plus 1 over n plus 1 for the antiderivative. And then we're going to evaluate it from x is equal to -1 to 2. That is the notation we would use. So I'll let you finish that one. If we have the integral of e to the x from 0 to 1, the antiderivative of e to the x is just e to the x. If you remember, the derivative of e to the x is e to the x. So we just need the e to the x, and then we're going to evaluate that from x is equal to 0 to 1. E to the first power minus e to the 0, and we have to watch that. So we get e to the first power minus 1, and there's your answer. Okay, so watch the input of 0, that it's not 0 in that case. So you should recognize that if you're thinking about for the antiderivative, whatever you find, then the derivative of that is going to be 1 over 1 plus x squared. So you probably recognize this one as arctan. So this is going to be arctan of just the regular x, because a is equal to 1 here. So arctan x, and then you would evaluate that from x is equal to -1 to 1. So you would see that you have the arctan of 1 minus the arctan of -1. So you kind of remember these. The angle whose tangent is 1 is pi over 4. Always radians, not degrees. Minus the arctan of -1 is going to be negative pi over 4. So we're just going to add these, and we get pi over 2 for an answer. So there's your answer there. Okay. Recognizing this one, you can kind of see that that's going to be an arc sine x, and then we're going to evaluate that from 0 to 1/2. So we would say the angle whose sine is 1/2 minus the angle whose sine is 0. So that would be pi over 6. Sine of pi over 6 is 1/2 minus the angle whose sine is 0 is just 0. So our answer would be pi over 6. And then for number 6, where you have the secant squared, so you're thinking what is the antiderivative of secant squared? So you're of course thinking about the trig function whose derivative is secant squared, so you know that that's going to be tangent x. And then you're going to evaluate that from 0 to pi over 4. So that would be tan of pi over 4, and then minus tangent of 0, and that's going to be equal to 1 minus 0. So your answer is 1. So as well, there's a carryover. We're getting scalars for an answer, but with all of these, if we were dealing with the graph itself for these functions, we would be looking at the area under the curve. And since we finished that one, we might as well finish this last one. So this is x cubed and evaluated from -1 to 2. So our answer is just going to be 2 cubed minus a -1 cubed. So that's going to be 8 minus a -1. So our answer here for this one would be just 9. Okay, so that's it for today's lesson. That'll finish everything up, and we'll see you tomorrow, I hope. And that finishes us up 5.3. You just have the 5.3 homework in My Math Lab. Have a great night. I'll see you when I see you.